All right, we're turning now towards descriptive statistics, and first of all we're going to deal with the measures of central tendency, and following that be measures of variability. So we can divide descriptive statistics into two main branches, the first being measures of central tendency and the second being measures of variability. So the measures of central tendency are showing where the center of the distribution is. In other words, where do most of the scores fall? On the other hand, the measures of variability are looking at the width of the distribution, how wide it is, how spread out it is, how dispersed the scores are. So I think that'll make more sense if we look at a real-world example, that is thinking about car costs. So if you look at this normal curve, and this is from a Consumer Reports product, it's showing here right in the middle what the market average is, and that's that 16,447. And then it shows the variability here between what some great prices would be, some really low prices, to some not so good prices that are above what the market is. And this distinction here between good and above market is kind of arbitrary. What we'd be interested in is this middle line showing the measure of central tendency, the mean, and then you can see that there's variability. Some people are going to pay over here on this end above market, maybe close to 17,000. Some people will get a deal down here, find the right place to buy it for 15,700 or so. So that's just showing you how those two things come together in the normal curve. Okay, and then just a learning check here, if we can look at these four distributions. So first off, I want you to try to figure out which one has the highest variability. Which color distribution has the highest variability? And you can pause it if you want a second to think about that. All right, so that would be this one. The one on the bottom here, what color is that? Orange, I guess. It's more spread out. See how it has all this variability here that the other ones don't have. And then the next question would be which one has the lowest variability? And you can pause it for a second if you want to think about that. So coming back, the lowest variability would be the blue one. If you can look at the graph here, it's not spread out very much. The scores are tightly packed in around that mean of 0. So it's taller, but that actually means it has less variability because you're stacking up more scores on the same small piece of real estate. All right, and next would be next question would be which one has the lowest central tendency? You can pause if you'd like. Well, the lowest central tendency would be the green one, because you can see that its mean falls below the mean of the other ones. All the other ones have a mean of 0. They're all centered on 0. The green one has a central tendency lower than that. Okay, then the last question is, how is the blue distribution different from the red distribution in terms of central tendency or variability? I'll let you think about that. Okay, coming back, the blue and the red differ solely in terms of their variability. They have the same mean, they're both centered on 0, but there's more variability in the red distribution than there is in the blue distribution. All right. The next point here is we can look at central tendency and variability together to see how they interact. And let's imagine that you're investing for 3 years and you're curious which stock would be the best one to invest in. And here you have two distinct options. Stock A, which is the blue line, based on these numbers, and stock B, which is the purple line, based on these numbers. Now, you might notice that it is true that stock A has a higher average. 8.3 is higher than 6.3, but there's a distinct disadvantage to A, which you might want to stop and try to think about before I say it. So you can pause here. What's the disadvantage to stock A? All right, the disadvantage is that it's nuts. It goes up and down a lot. There's a ton of variability. It has a large standard deviation, almost 16, meaning that from year to year it can rise or fall. you'll notice that in some years it actually loses money because it crosses below 0. Stock B has not quite as good a return, 6.3 versus 8.3, but it's pretty steady and it never dips down below 0. This suggests that for the short-term investing, you might be willing to sacrifice a bit of return for stability. So that's how one way we can think about those two key dimensions of distributions interacting. All right. Going to take a second here to talk about the relevance of descriptive statistics to inferential statistics. So descriptive statistics are the ones where we're simply describing what's going on in a distribution. We're giving a mean, a central tendency, talking about a range, maybe talking about the variability, the standard deviation, but we're not going beyond the numbers. We're just stating the numbers. With inferential statistics, you're trying to make a decision. Typically, you're trying to make a decision regarding a hypothesis. You're either going to reject or retain it. And you could be wrong. You're making an inference based on the data you see. So we'll cover descriptive statistics now, and then we'll get to inferential statistics later. But I want to give you an example where the inferential statistics come into play. And I'm doing this so that it makes sense to you why we're covering means and standard deviation. So if we think about the outcome of an experiment, and our key question is, did the independent variable affect the dependent variable? We need to consider both the difference between the means and the amount of variability. So let me show you what I mean. Let's imagine a study with two outcomes, and we're going to see the importance of variability here because it affects the kind of inferences you can draw, the kind of conclusions that you'll reach. So the example is, imagine there's a business where customers are routinely offended. You might have comments being made about the customer's mother, your mama's so fat, yada, 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 or miscellaneous name calling. Can I call your son stinky? And you're thinking, boy, I need to fix this. So you're going to do some social skills training for your clerks to try to improve their customer service. So the independent variable, the thing you're manipulating, the thing you're changing among the groups, is to either get training or no training. Those are the levels. The dependent variable is how satisfied customers are after an encounter with one of your clerks. So let's imagine two different worlds where we get two different outcomes. So in version 1 here, you have the control outcome and the experimental outcome, the same in version 2. So here in version 1, you'll notice there's a difference between the two groups, and there's a difference between the two groups over here. So if you look at the next slide, it has some questions we can ask. So the first one is asking you to think about whether the control and the experimental groups differ, both in version 1 and version 2. And I think we can say they do. And if you notice the size of the difference is about, or exactly, is 1. Experimental people, the people that had the training, did 1 point better than those that had the control. That's true in both version 1 and version 2. Another question, though, is there a difference in the amount of variability? If you look over here, the standard deviation, which we'll get to in a minute, and again, it's just the typical amount of difference we'd expect from a given score from the mean. There's tighter variability over here than there is in version 2. In other words, if you look at these scores, they're falling closer to the mean of 3 than their counterpart over here, where they're falling farther away from 3. The average is the same, but there's more variability. Same here if you compare the experimental on the version 1 to the experimental in version 2. So the scores are more spread out here. There's more error here. So which version appears more reliable? Well, here's a hint. Think about variability by another name, error. There's more error over here. So we're less confident that that mean of 3 or that mean of 4 is going to be stable if we do the study again, if we collect more data. The mean of 3 here and the mean of 4 here are more likely to be stable in version 1. Where would I be more confident in obtaining a similar result? Well, it'd be here in version 1. All right, let's cover now 3 basic ways that we can talk about the central tendency of any given distribution. So I've just constructed here an imaginary distribution where you have some friends, or excuse me, you have the number of close friends somebody reports, different people report. Start that again. All right, now let's look at the three options we have for the measures of central tendency: the mean, the median, and the mode. And we'll look at these in relationship to the data here we have, where we ask people to indicate the number of close friends that they have. So the mean is the most arithmetically sophisticated measure because it considers the value of each and every score. We get it by taking all the scores, adding them up, and then dividing by n. This is the one you typically think of when people talk about what's the average. In terms of a sample, X with the bar over it, or capital M, would be the symbols. With a population, it'd be the Greek symbol mu, which is pronounced mu. One of the characteristics of the mean is it's the best predictor of a given score if no other information is available. And you'll also see it come up when we calculate deviation scores. So if I figure out the mean for these numbers, all I do would add these up, and it works out to a certain sum, divide by the n here, and it would work out to 4.36. By n, I mean the number of scores. All right, next, the median is simply the score at the 50th percentile, the score that's in the middle. So if you think about 1 and 12 are the farthest out, 2 and 6 are next, 3 and 5 are next, 3 and 5 again are next, 3 and 4, and the middle score will work out here to be 4. That's the score at the 50th percentile. It's in the middle position. The median has the characteristic of being less influenced by skew, and so that becomes a preferred measure of central tendency if the data is not symmetrical, if it's skewed. Then last, the mode is the most frequent score. Oh, excuse me, let me back up. So with the median you'll note here is 4. It does a better job of staying close to the center of this distribution than the mean, which gets pulled by this 12. So you can see that the median here is better because of this extreme score causing skew. The mode is simply the most frequent score. So in this distribution, the mode is 3. The mode is particularly useful if the data is qualitative. In other words, if I ask you what your favorite movie is, and I ask a group of people that question, the best I can do to talk about where the data are centering is to just report the TV show that came up the most. It's also useful if the data is bimodal, meaning it has two distinct centers, and I'll show you what that means here in a second. Okay, so here's how skew affects measures of central tendency. If you have extreme scores out here, it'll pull the mean far away. So the joke I say is, imagine there's an evil temptress out here and it's saying, "Come here, Mr. Mean, go this way." And the mean gets confused and wanders off towards the evil temptress. The median, on the other hand, moves a little bit that way potentially, but takes more of the stance of talk to the hand. The median is not going to mess around with the evil temptress. And then the mode would still be the most frequent score, which is the one that's at the very top here, the most frequent score. Here's another demonstration of how skew affects measures of central tendency. Again, you see how the mean gets pulled out the farthest, the median next, and the mode hangs in the middle. If there is no skew, the mean, median, and mode will all line up exactly on the in the middle of the symmetrical curve. Okay, and then as promised, here are some examples of bimodal distributions. This is what it would look like on a histogram. So perhaps these are some measures of strength where we're comparing athletes who engage in some kind of official conditioning training with weights, and then the rest of us who are just maybe laying on the couch as our main form of exercise. And you'd see that there'd be two distinct distributions underlying this one single distribution that gets the bimodal thing going on. Another example here would be nicotine use. You might have some people that use no nicotine on a daily basis, and then those that are serious smokers, and then maybe some people that are so-called party smokers that are just dabbling in the dark arts but don't partake on a regular basis. Here's an example from a Human Factors website where you're trying to design things for different body types, and this is comparing, this is some older data, but women in the Air Force and men in the Air Force. And you can see that the distribution of height for women is substantially less than the distribution of height for men. And this distribution is bigger simply because it has a larger N. It's based on more people than this one. So in both of these cases, or in all three of these cases, the mode will let you get at these distinct humps in the distribution. Okay, then we want to choose the best measure of central tendency with the following data. So if you imagine having a number of close friends as the question we ask, imagine it turning out either one of these three ways. So first thing I want you to do is hit pause and think about which measure would be best for A, B, and C, and then start the video again when you've decided. Okay, well, for A, it would be the mean. The data are not funky in any way, to use a technical term. There's not a skew, and it's not bimodal. So our default, the one we prefer, other things being equal, is the mean. And B, there's one weird score. This person is way too social, right? 27 friends. They probably have a Twitter account and several Facebook pages, maybe multiple personalities. Something's different here than the rest of it. So we'd want to use the median because it'll be less influenced by that skew. And then here, in this last group, the mode would be most appropriate. There's two groupings of data, right? This group and this group down here, one with the mode around 3 something and one with the mode around maybe 12 something. Okay, so the next thing I would like you to do is hit stop and actually calculate those three measures as we just indicated for those three. And we'll check your results here in a second. Okay, before I show you those, just let me show you how I got my answers. I just used the computer. You went to SPSS and you go to Analyze Data, go to Frequencies, go to Analyze, Descriptives, and then Frequencies, and you'll get a chance to just move these over. And when you do the frequencies, you want to hit the statistics and choose mean, median, mode, and oftentimes it's good to get standard deviation as well. And here would be the output for those three data sets, A, B, and C. You can see this is what you should have calculated for the first one, the mean of 2.91. You would just add up all the scores and divide by N. For B, that was the one that had the weird high score. You can see how the median was the one that was the best there, and it's not nearly as high as the mean. And that you just get by figuring out what the middle score is. If it works out that it's between two numbers, say like between a 3 and a 4, if you have an even number of data points, then you would just take the average and it becomes 3.5. And then last, the mode, you can see there's it has a little notation here. There's two modes, so one of them would be 3 and the other one I think works out to 12. So that's that. Okay, the next one I'm talking about the difference between samples and populations. So statistics characterize samples. So for example, the mean, or S, which is the symbol for standard deviation, are characterizing statistics. Parameters, in contrast, characterize populations. So mu and sigma would be parameters. You'll notice that parameters are always Greek symbols. Statistics are always regular alphabet symbols. And one way to think about this that I think helps is that statistics are striving to estimate the population parameters. They're trying to, from the sample, make a determination about what's going on in the population. So let's look at pretending that we want to know what the average SAT verbal score is at Winthrop. So let's pretend that we don't know this, but let's say that if we could look at all the scores, we'd figure out that the average indeed in the population is 493. All we can do, though, is take a sample, and let's say we take a sample of 6 people, and we figure out their mean is 503. Now you'll notice that there's a difference between the sample and the population, and that difference is called sampling error. In other words, when you reach into this pot and pull out 6 people, it's very unlikely you're going to exactly replicate the true population mean of 493. Typically there's some error, we call that sampling error. If I were to take another sample, I might get another number. It'll probably be not too far off from the mu, but it's going to be somewhat different. And almost every sample then will show sampling error. And just to be clear, we hate sampling error because it makes it harder to do our job of figuring out what's going on in the world when we always have this error to contend with any sample we deal with. And obviously, the reason we're typically dealing with samples in psychology is we don't have the resources to go out and measure every single person in the world. All we can do is measure some people, then try to make an inference about what's going on in the world. Okay, now we have samples and populations in experiments. This will make it a little more clear why it's important to know this distinction. Typically, we don't know the parameters. There's certain situations where we might, but typically in a regular study, we have no earthly idea what the mu's are. All we can do is make inferences about the mu's based on the sample means, the capital M's. So let's imagine an experiment where we're trying to improve reading scores in a group of students that, say, aren't doing as well. This would be the kind of activity a school psychologist might be interested in. So we imagine the intervention group, that is the group that we mess with, and the control group. The independent variable is whether or not we intervene, and we're going to see if there's a difference on the dependent measure of reading scores. So in the intervention group, we pull out 5 people, and we measure the reading scores. In the control group, we pull out 5 people, and we measure the reading scores. And that gives us the means of 33 and 38. So we are curious. What does this really mean about the population mu's? Is there a difference in these two groups based on the way we treated them? Well, it's as if there's a curtain that hides or occludes what the true score is, and all we can do is make judgments based on the means. If one way of thinking about it is that God knows what the true means are, but we don't. All we can do is look at the data. So questions we ask, is this difference reliable? And we'll get to this later in the course when we deal with inferential statistics like the t-test, the z-test, the f-test, and others. Another way of saying that is there a treatment effect? If we decide there's a treatment effect, we're saying the intervention really does make a difference, and it raises these scores relative to folks that don't get it. That's what a treatment effect would mean. Another way of asking that, or stating it, is do the population means really differ? That is, did those folks who get the intervention walk away with a higher reading score, a higher true reading score than those who don't get it? Or is the difference simply the result of sampling error? Because it could be the case that if we pulled more scores out of here and more scores out of here, that these means would change and they might converge. And if they converge, that means there's no difference between the two groups, that the experiment failed, that the intervention had no effect on reading scores. And that's it. Next, we'll talk about measures of variability. Thank you.